was that we're trying to go to this new definition of what the derivative is. And the reason that we even have a new definition is because mathematicians are so darn precise. There can be no estimating what a number is. There can be no disagreement about what the right answer is. So the kinds of approximation techniques that we have in order to kind of estimate derivatives are not good enough because it's possible for two people to disagree. But this definition right here is based on the idea of the small intervals that we did, estimating using small intervals. Look, if I take the slope of a secant line, but I get this movable point so close to the other one that I can really tell what the limit is, I can really tell where that number is going to, then I can use this as a limit definition, or I can use this as a derivative definition. Okay? So we talked about arrow notation and how that was kind of like this idea they gave you, hoping to make limits easier. And we talked about when limits exist and when they don't using the picture. And we decided that the two ants have to be coming together to the same y value. They have to go to the exact same place on the two sides in order for the limit to exist. This one does exist, and this one does not because we don't allow those jumps, okay? All right. So let's go ahead and talk about the real limit notation, all right? This is how we really do a limit. To say that the limit as a function f of x, the limit of a function f of x as x approaches a, we write, here it is, we write that there's a limit as x approaches some value that you get to choose, right? Some actual number, this is a parameter, of f of x, and we can go ahead and call that, let's call it scripty L for a second, okay? Just for a second. So a is a number, L is a number, and it's a y value. And the rest of the notation tells us what function we're working with and where the independent variable is going, right? So when we look at our charts and we're taking little tiny intervals around, say, 2, then a would be equal to 2. This is always the goal on our charts. When I was doing my notes on this, I would always put this number in a box, right, to show you what that was. So the first thing that we're going to do is we're going to use this real limit notation, and we're just going to write out some stuff here. So what I'd like you to do, notice that this function is y is equal to f of x, okay, so that's the name of the function. I'd like you to write the 4 limits, 1, 2, 3, 4, for all 4 of the x values here. And we're just going to write in the notation and go to the next thing, okay? Because honestly, you know, for x equals 1. You guys, so this stuff is just, you know, it's quick to write down, and you could probably think about it forever to think about what to write down, but at least we can try and get into it and, you know, give you guys a sense of what's going on. So we're using this purple limit notation, you can't even see that, purple limit notation up here, and we're just going to rewrite all of these limits in that notation. So for x is equal to 1, I want to write the limit as x approaches 1. Okay, because that's my special value. Of f of x, because this function is called f of x, and that's equal to, what is the limit here? Where do the ants think they're going? Perfection. Okay, so for x equals 2, I'm going to do the limit as x approaches 2 of f of x equals, what is it? It is not 2, it's only 2 on the left. Is it 3? It's only 3 on the right. See how if you come in from the left, here's my ant, here he goes. Yeah, and here's this guy over here. He's another ant. Oh, God, he looks terrible. Anyway, so they had a hard night. But it doesn't matter, because coming in from the left, this guy thinks he's going from 2. Coming in from the right, this guy thinks he's going to 3. They don't agree, so there's no limit there. Does not exist or undefined, something like that. Okay? For x equals 3. I heard some controversy about this. What do you guys think? You think it's 1? Well, it's about 1, right? This is actually the total easy version of doing a limit, is when there's no problem with the function at all. You can still have an ant come in from both sides. And the function value is just, the limit is just whatever the function value is. So we'll call it approximately 1. Notice what I've written here. The limit as x approaches 3 is just the same as the function value at 3, because that value does exist, right? There's no break in the graph and there's no ambiguity about what that would be. And we think it's about 1 reading it off the graph, okay? So that's a really nice dense piece of notation. How about for x is equal to 4? The limit as x approaches 4, f of x is equal to 2. Thank you so much. Perfect. 2. This is what a limit does. It plugs holes. Doesn't matter if there's actually a function value there or not, as long as it's just one hole and the ants think that they're going to get to the right place, then it's cool. Megan. That answered my question. Woohoo! All right. Nice. All right. So now what we're going to do is we're going to do some basic limit computations. I love these because this is how we're going to actually do a little bit of derivatives that are actually mathematically correct, right? We're going to take a function, we're going to figure out some derivatives that are mathematically correct. The first 2 of them, I want you to notice, are examples just like x is equal to 3 up here, meaning that there's no problem plugging in 2 into a quadratic equation. Quadratic equations just exist everywhere, okay? So this limit is just going to equal the function value at 2. Similarly here, sometimes it's an issue plugging in 0, but for this particular function there isn't an issue plugging in 0, and the derivative is just going to be, or the limit is just going to be equal to the value when you plug that in, okay? So this is the easy kind of computation to do. Just really quick, go ahead and do that. Okay, folks, so this one is so straightforward. Because this is a polynomial function, polynomial functions have no breaks, no gaps, no holes, no asymptotes, no anything that's a problem, okay? So this is just going to be equal to the function value if you plug in 2. And that's equal to 2 squared plus 2 times 2 minus 4, otherwise known as 4, okay? So the limit, if there's no break, gap, jump, or other crappy thing happening with your function, is just the function value. So on this one also, this is going to be equal to the function value at 0, which is just 0 squared plus 1 over 2, otherwise known as 1/2. Are we good with that? Do you see what I'm saying? And do you see how it resembles number 3 up here, or the x equals 3 up here? There just wasn't a problem, so we just used the function value for the limit. Yeah?
Was the, for x equals 3 on the top part not computed for the
Yeah.
part? Was it supposed to be f of 3 is approximately 1, or is it supposed to be f of 1?
Yes. Sorry, thank you so much. The function evaluated at 3. And you know what? Talking and writing at the same time, I sometimes get into trouble, so I apologize for that. Great. All right. So now what I'd like you to notice about these 2 examples down here is that they are exactly the same. Take a look at this side by side, you guys. They are exactly the same as this limit definition for the derivative that I've done. So the first one is actually computing the derivative of x squared plus 1. It's actually mathematically computing that derivative. And this limit over here is the derivative. Oh, I'm going to do it in your new notation that you're about to learn. It's the derivative of 2x minus 3. We're about to learn this notation, but it just means the same thing. Derivative of 2x minus 3. Okay? So we're actually going to go ahead and compute the derivatives of these computationally just the way that they do, you know what I mean, in the hard calculus classes where it's really computational, like the engineering calculus and stuff. This is how they teach students and how they work with it. So what we're going to do here, and the philosophy is always the same, and this is the hardest kind of problem you'll have to do, and you know, you're always going to work it out the same way. Notice that the top is one of those simplify problems that we've had a couple of times coming in, right? So you're always going to go ahead and simplify this f of x plus h minus f of x. Remember all those problems we've done? Okay, you're going to simplify that first. When you've done that, you're going to be able to cancel the h out. And at that point, there will not be any problem plugging in a 0, because the only problem with plugging in a 0 is that it gives me a 0 denominator here. So once I cancel h's from the top and the bottom, you'll just be able to plug it in and evaluate the limit. So this is going to be kind of, in a way, easy. But I'm going to do the first one for you if you'd like. Would you like that? Is that a positive thing? I mean, I'd rather you work on your own if you can, but if you feel like it would suck, then let's not. The one thing that students always hate about these problems is you have to write the limit down until you actually plug in h is equal to 0. So you have to keep on writing this limit notation for a while, and that kind of sucks, but you'll get used to it. On the top, I'm just going to simplify. So I'm going to square out my x plus h squared, so that's x squared plus 2xh plus h squared plus 1. And I'm going to distribute my minus into my, my parentheses at the end. So minus x squared minus 1. Does everyone see where I got that line from? Yeah? Okay. I hope. Maybe you can ask your group in a second if you didn't actually get it but don't want to confess. Gosh, I hate that though. Why wouldn't you just confess? Okay, so now I can remove the parentheses here. X squared plus 2xh plus h squared plus 1 minus x squared minus 1. All right, magic happens here. Do you guys see the magic? Yeah, what is the magic? X squareds cancel? The 1's cancel. Okay, so this is what I'm left with. I'm just writing a million steps to try to really make it clear. 2xh plus h squared over h. Now be careful here. Oh my God, I'm going to put some stars. Be careful on this step, because you could have done all this work perfectly, but the problem is that a lot of students tend to incorrectly cancel their h's, and I really need you to caution you to take that extra minute and write down another step, okay? What I need to do is factor an h out of the top. And only when I have a factor of h can I then cancel. So this is going to be the limit as h approaches 0 of h, 2x plus h over h. Do you see what I've done? I've just pulled an h out.
Yeah.
Now I can cancel my two h's. And you can plug in h is equal to 0 up here. It makes no difference. The answer is 2x. Now 2x is the function derivative. Do you see what I mean? It is the derivative as a function. So if you want a derivative at any specific value x, what you do is you put in that x into here. If you want the derivative at x is equal to 4, you plug in 4 and you get 8. Okay? So this is the derivative function, and that's why it's so powerful. And not only does the derivative at a given point, but any place you want. Jack. But then you plug in h is equal to 0. Yeah, totally. So I could write that line, the limit as h approaches 0 to x plus h, but then you just plug in h is equal to 0, and that's your final answer. Good. Did I get yours too, Zach? That's all right? Okay. Okay, you guys, the answer here is 2. Woohoo! It's 2 at any point. And why is it 2 at any point? Okay, it's not about h's canceling out. Oh, okay. Now wait a minute. This isn't a horizontal line, but tell me about your original function. It's a linear function. And the derivative of a linear function is always just the slope of that function. So 2 is the slope of 2x minus 3, so I totally expect the answer has to be 2. But now I've proved it, like mathematically. You know what I mean? It's like rigorous mathematics. It's proved, it's done. Should we do this problem together, or are you guys comfortable with it and we can move on? You want to just do it? Oh, okay. All right. So what we're going to do is we're going to write the limit as h approaches 0. You guys, this is a half a point because your notation's not correct unless you write the limit until you take it. All right. This is a really clear thing. And then I'm just going to do one step where I simplify the top. To simplify the top essentially means distributing twice. I need to distribute my 2 and I need to distribute my negative 1. Can I do those both in the same line? Is that all right? Okay. So I have 2x plus 2h minus 3 minus 2x plus 3. Be careful of that plus 3 on the end. That's a really obvious place to make a silly error, right? Magic happens. What's my magic this time? The 3's cancel, the 2x's cancel. So what I have is the limit as h approaches 0, write that, okay, make sure, of 2h over h. In this case, the h's are obviously factors of the top and the bottom because there's no pluses or minuses. If there's no pluses or minuses, you're pretty much home free. So the limit is equal to 2. Okay, just as I promised, the limit's equal to 2. Okay? Yeah.
How would you write that for your answer? Would you just say 2? Or?
You know what would be awesome? F prime of x is equal to 2. The derivative in this case is equal to the limit of this difference quotient. That's why I care about these problems. You know what I mean? This is how you officially do the derivative. So my derivative of my function is equal to 2. Perfect.